This video covers solid-state physics, specifically crystal physics. We'll be discussing the lattice, crystal structure, and the Bravais lattice. A lattice in solid-state physics is a regular, repeating three-dimensional arrangement of points in space. Each point marks the position of an atom, ion, or molecule in a crystal. Simply put, a lattice is a geometrical pattern showing how particles are arranged in a solid. When atoms are arranged in a regular repeating pattern, they form a crystal lattice. Examples include common substances like sodium chloride, diamond, and quartz. These substances possess well-defined lattice structures. Lattices can be one-dimensional, where points are in a straight line. Two-dimensional lattices have points arranged in a plane, like a sheet. Finally, three-dimensional lattices, which resemble real crystals, have points arranged in space. A lattice point is the specific position in space where an atom or molecule is located. The diagram illustrates how these points form a unit cell, the smallest repeating structure. A space lattice is defined as the three-dimensional arrangement of lattice points within a crystal. All real crystals exhibit a 3D space lattice structure. The unit cell is the smallest repeating part of a lattice. When this cell is replicated in all directions, it constructs the entire crystal structure. Every unit cell is characterized by its lattice parameters. These include the side lengths A, B, and C, and the interfacial angles alpha, beta, and gamma between them. The crystal structure is formed by combining the basis, which is the atomic or molecular group, with the lattice, the geometrical arrangement of points. There are three primary types of cubic unit cells: simple cubic, body-centered cubic, and face-centered cubic. These differ in how the atoms are arranged within the cubic structure. This table summarizes key characteristics of the three unit cells, including the total number of atoms and the coordination number for simple cubic, body-centered cubic, and face-centered cubic structures. In a simple cubic structure, atoms are only at the 8 corners, resulting in one total atom per unit cell and a coordination number of 6. Polonium is the only element that naturally forms this structure. Since the simple cubic cell has no atoms in the center or faces, it is also called a primitive cubic cell. Each atom in an SC structure touches 6 neighbors: up, down, front, back, left, and right. The body-centered cubic, or BCC structure, has atoms at all 8 corners plus 1 in the center, giving 2 total atoms per unit cell and a coordination number of 8. Examples include iron at room temperature, chromium, and tungsten. The BCC structure is defined by 8 corner atoms and a central atom. The coordination number of 8 is clearly visible, as the center atom is connected to all 8 corner atoms. The face-centered cubic, or FCC, structure has atoms at the 8 corners and 6 face centers, totaling 4 atoms per unit cell, with a coordination number of 12. Common examples are copper, silver, aluminium, and gold. The face-centered cubic cell, or FCC, is a cube unit cell. It contains 8 atoms at the corners and 6 atoms at the centers of the faces. This diagram illustrates the FCC structure with 8 corner atoms and 6 face-centered atoms, resulting in a coordination number of 12. Packing efficiency is a key measure. Simple cubic has the lowest efficiency at 52.4%. Body-centered cubic is moderate at 68%, and face-centered cubic is the most efficient at 74%. Lattices are important as they help us understand the structure of solid materials and explain properties like electrical conductivity and hardness. They are fundamental concepts in solid-state physics. Crystal structure is important because it determines the density of a material and affects properties like electrical and thermal conductivity. It also dictates hardness and strength. In 1848, French scientist Auguste Bravais proved that only 14 types of lattice structures are possible in 3 dimensions. These are known as Bravais lattices. The 14 Bravais lattices are classified into 7 crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. The cubic system includes 3 types: simple cubic, body-centered cubic, and face-centered cubic. The tetragonal system contains 2 types of Bravais lattices: simple tetragonal and body-centered tetragonal. The orthorhombic system includes 4 types: simple, body-centered, face-centered, and end-centered. The monoclinic system has 2 types: simple and end-centered. Both the triclinic and hexagonal systems have only 1 Bravais lattice type each. Finally, the rhombohedral system also has only 1 Bravais lattice type. Bravais lattices are crucial for classifying all crystal structures, explaining the atomic arrangement of materials, and are fundamental to solid-state physics, particularly in X-ray diffraction studies.